the development of quantum theory. The quantum theory began with observations, and the observations were these unexpected light patterns that emerged when you tried to build a hydrogen lamp. A hydrogen lamp is just, it's got electrons. Electrons get excited and emit electromagnetic radiation, and they expected a continuous spectrum. And, continuous spectrum would give white light, but what they ended up with is this purple light. And when they analyzed the purple light, it consisted of specific lines. That is, they didn't see the rainbow colors, they just saw specific colors, and each of those colors corresponded to a discrete line. That discrete line would have a wavelength associated with it, and a frequency, and an energy associated with it. And so it wasn't just red light, it was just one specific energy of red light. And the same thing with the green, the blue, and the violet. It turns out that each element has a unique line spectrum, so it's like the fingerprint of the element. And so it wasn't just for the hydrogen. When they tried to build lamps from other elements, they saw that they got these lines. So these last two topics I don't want to talk about just yet. I don't know why they put it in this slide here. And so let's take a look at the spectrum. And so here's our continuous spectrum. And in a continuous spectrum, all the colors of the rainbow are observed. And that means all the energies of light, from low energy, red, to higher energy, violet, are present. But over here, we're missing a lot of colors. In other words, we're missing a lot of energies of light. And so the blacked out regions are called forbidden energies. And what we see, we only have one allowed energy here that corresponds to wavelength. The wavelength is well known. And the green line here, a blue line and a violet line. So we observe this unusual pattern. This is reproducible. Each time you build a hydrogen lamp, you get the same pattern. And so what do you do next in the scientific method? There is a pattern there. Then you look what? What do you do next usually?
Hypothesis?
No, before the hypothesis. You observe and then you find the pattern and then you describe the pattern. Like we could say there's a pattern. We see this pattern here, but what we want to do is we want to be able to describe the pattern in the most concise definition possible, which would be what? What's the most concise definition for a pattern that you can have? No, theory comes at the very end. A law, right. A law is usually an empirical equation. Does anybody remember what empirical means? It's a very common term in science. What's that?
It's not derived from theory, it's derived from evidence from observations.
Right. It's a mathematical equation derived from observation. So this fits a mathematical pattern, actually, the numbers here. So if we list the numbers either in terms of energy, wavelength, or frequency, that fits a mathematical pattern. That mathematical pattern we call a law, and the law for this is the Rydberg equation or law. Rydberg law is not described in this book, so I'm going to skip it, but the mathematical pattern, this is the hydrogen spectrum here. So the violet line is very weak in color. The top one's hydrogen. And we see the 4 lines here in the line spectrum. And this is a fingerprint for hydrogen. This is how they can tell the sun. You know, the sun is made up of primarily hydrogen because you see the distinct emission lines for hydrogen. In the sun. Although the sun, you know, the sun emits white light. And what happens is some of the colors of the rainbow are missing because they're being absorbed by the hydrogen that's present in the sun. And so, actually, maybe we could take a look at the solar spectrum here. So when you look at the solar spectrum is pretty much all the colors of the rainbow are allowed, but there are certain colors that are missing, and these colors correspond to certain elements that are absorbing. So hydrogen is absorbing a lot of the light here. This is sodium is absorbing here, some other elements here. And so when you look at these, in the solar spectrum, yes, it's white light, but there are certain things that are missing. Those certain things that are missing are being absorbed by the elements that are present there. And so this is little fingerprints. So based on the pattern of the lines, we can figure out what elements these are, because hydrogen has a certain fingerprint, helium has another fingerprint, so you'll find helium here as well, and others.
So is the light from the sun white light?
I'm sorry, the sun is white light, and so, yeah, essentially it's not perfect because there's something that's missing, but essentially it's white. I mean, that's so little of the spectrum that's missing. It looks white to us. You know, it has different intensities. This is the intensities here, depending on how much light is emitted. All right, let's go back to the PowerPoint here. You can see that mercury has a different pattern. Neon has a different pattern. So the mathematical pattern that's for hydrogen is the Rydberg equation, but the Rydberg equation, the Rydberg law doesn't work for mercury, it doesn't work for neon. There's a different mathematical pattern to those. But they were just focused on the hydrogen, trying to figure out hydrogen because hydrogen is the simplest. And so hydrogen gives kind of a purple. Neon kind of gives an orange light. So if you add up all these lines, it appears orange. The light, orange, red, or whatever the neon lights look like. So you can make a neon light bulb, but it's not white light. It was expected to be white light, just like hydrogen. When you make a neon lamp, it should have been white light, but it wasn't. So something's going on here. What's going on here is that there are forbidden energies and allowed energies for the electron in an atom. And so the next step would be, okay, so we're looking at hydrogen. The next step would be to come up with a hypothesis. Can you come up with a hypothesis why there would be allowed and forbidden energies for the hydrogen atom? And so Bohr came up with a hypothesis. But it turned out Bohr's hypothesis is wrong. And so this is history of the development of quantum mechanics. So since you have to know a little bit of history, even though Bohr's hypothesis was wrong, we're still going to take a look at Bohr's hypothesis. So the Bohr model of the hydrogen atom. Atoms consist of a dense nucleus. Yeah. The electrons are outside that nucleus. But basically, the Bohr hypothesis is this. The electrons travel in orbits around the nucleus. And so the Bohr model is electrons orbit around the nucleus, like planets orbit around the sun. But these orbits are spherical orbits. They are not planar orbits like planetary orbits. You know, they could be in any plane. When we think about orbits, we think that we can have any orbit, you know. All you have to do is, if you want a closer orbit, you slow down, and then you'll get closer, like Earth's orbit, a satellite. Or if you want a further orbit, you speed it up. But normally orbits, any orbit's allowed, you know. It just depends on how fast you're going, how much energy you have. That's going to dictate it. But in the Bohr model, not any orbit is allowed. You know, normally when we think about an orbit, we think about the radius, you know, how far it is from the center. But in the Bohr model, certain radii are not allowed. The electron can only orbit at certain distances or certain energies from the nucleus. We call that quantized energies because quantized is there's discrete energies that are allowed and then there are energies that are forbidden versus continuous. Quantized versus continuous energy. So one analogy that people use to talk about quantization of energies is to look at gravitational energy. You know, here we have a continuum of gravitational energies that are allowed because, you know, the higher up you go, the higher energy you'll have, higher potential energy you'll have. And in something like this, all energies are allowed because you can step up a little bit or you can step up a lot. Here. Whereas if you look at the stair steps here, there are forbidden energies. So the first allowed energy would be, actually the first allowed would be here, 0, but we'll call it the first step. And so we say that this is n equals 1 is allowed. N equals 2 is allowed. So let's say this is 1 foot, this is 2 feet, something like that. Over here, n equals anything is allowed. We could be 1, we could be 1.1, 1.2, any distance up to the second step. Here, these are discrete or quantized gravitational energy levels. And so what's thought to happen is the electrons thought not to be continuous like this. If we're continuous like this and the electron can orbit at any distance, what we'd expect is a continuous spectrum. The electron's got to behave like this. It's got a stair step. If it stair steps like this, then there are forbidden energies, any energy in between these two steps. And these two are forbidden. But these are the allowed energies here. And so the most important thing in Bohr model is the energy of the electron is no longer continuous, as it was expected. The energy of the electron is quantized, we say. And so how does that look? How that looks is like this. This would be the first step. And so electrons here, it's close to the nucleus, so it's lower in energy. The further electron gets from the nucleus, the higher the energy. But it turns out like not every energy is allowed. So for example, we could be at the first step here, and the next energy that's allowed is the second step. But nothing's allowed between the two. And so this we call the first Bohr orbit, which would be n equals 1. The second step would be n equals 2, third step would be n equals 3, but nothing in between. And so we can't have 1.1, etc. All right, each of these corresponds to an energy. We can calculate the energy based on the radius, and the radius are given by these. The radius are quantized as well. The mathematical equation, do you see these numbers here? when we look at these numbers, these are quantized as well. And there is a mathematical pattern here. And so we're going to call this one R0. This is the first orbit, or R1. Let me call it R1. This is the first orbit that's allowed. Okay, this is R2 here. And so it turns out that R to the n is just equal to n squared R to the 1. And so the mathematical pattern is kind of interesting because here n equals 1, so 1 squared is 1, that's just R1. This one is R2. R2 is equal to 2 squared times R1, which would be 4 times R1. So if you take 0.5292 times by 4, we get 2.1168. This one here is R3, which is equal to 3 squared R1, which is 9 times R1. So if we take R1 and multiply by 9, we get this number. And this one's R4, which is going to equal 4 squared R1. So we see this mathematical pattern that comes up with these numbers here. And this would be a law. This would be the law of the Bohr orbits, we say. A law would just be some mathematical equation. R sub n is equal to n squared R1. And that would be the empirical equation that describes the orbits here. Actually, these orbits go all the way to infinity. But when we hit R infinity, what happens is something weird. And so we go up to n equals infinity. Then R to the infinity is equal to infinity squared R1. And what we say is this is equal to ionization. That is, the electron is infinitely far from the nucleus, so the electron and the nucleus are no longer attached. I say an electron's been pushed out to infinity. It doesn't have to go to infinity to lose the electron. You know. We can have ionization occur at shorter, effectively ionize it. Shorter distances. Well, it'll be an electron. Well, electron's got to go somewhere. It could go elsewhere. And so, I suppose if there's nothing else present, then yeah, bring it out to infinity. And so what we see here is that n goes from 1, 2, 3, ... all the way to infinity. So it's an integer. These are allowed. Everything else is forbidden. And so we see quantization occur, first step, second step, third step, but nothing in between. This is what we see in the mathematical pattern here. Over here, the same mathematical pattern exists. Do you see these numbers? Do you see the mathematical pattern in these numbers? Probably not, because it takes time to figure out the mathematical patterns. But there is a mathematical pattern here. And the mathematical pattern here is, we call this E0, or not E0, E1, sorry. That's for n equals 1. This is the lowest energy state. And then a little higher energy here is this one. This is E2. E2 is equal to, the mathematical pattern comes out like this. It's 1 over n squared E1. And so this would be 1/4 E1, or 1 over 2 squared E1. This would be E3, which would be 1 over 3 squared E1, etc. And so the mathematical pattern for this is E sub n. The energy at the nth step is equal to 1 over n squared E1. where E1's given here. E1, this is times 10 to the minus 18 joules. Times 10 to the minus 18 joules, that seems like an awfully small amount of energy, and it is, but you have to consider that's all in one atom. So this is actually quite a huge amount of energy. If we had a mole of atoms, you know, that these energies would be on the order of like 2,000 kilojoules per mole. It's a lot. So we get these equations that can describe this, and then we can make predictions. With these. And so let's take a look. The electrons can jump from, we don't call them jump, we call them transitions. And so the electrons can transition from one step to another step. The movement of an electron within an atom from the one energy level to another without passing through. The electron is normally found in its ground state. The ground state is the lowest energy possible state, and then we have excited states. And so electrons can get excited to higher energy, what we call energy levels. So this excited electrons are unstable. Eventually they're going to fall back down. You know, they don't stay at high levels. They'll fall back down. And as they fall back down, they emit energy because energy is conserved. And so they emit photons of light. The energy released appears as a line spectrum of the element corresponding to the frequency of the wavelength. These you don't have to worry about too much. But the pattern, the mathematical pattern looks like this. The steps aren't even like the steps of a staircase. The first step is a big jump here. And then the next step, n equals 3, is the smaller, much smaller jump here. N equals 4 is smaller. The steps get smaller and smaller progressively. And eventually what happens is, even though we can go to n equals infinity, the energy converges. But the radius diverges. And so what we're going to see here is that as we continue to go up here, the energy is going to converge. And so these energy levels are going to get tighter and tighter and tighter. And eventually what happens is we'll converge at n equals infinity. At n equals infinity, E sub infinity is equal to 1 over infinity squared E1. 1 over infinity squared is going to be 0. And so the energy at infinity is 0 joules. And so that's our 0 point, and then we go down lower in energy. That's the energy of the electron. When the electron's infinitely far away, let's do this probably in a different color here. R infinity is going to equal infinity squared times R1, which is going to give us infinity. The units are usually in, let's see, what were the units they used for R1? Go back and take a look. They use meters times 10 to the minus 10 meters. And so this would be infinite meters away. So, in other words, the energy converges to 0. The radius diverges to infinity. So, this is what we observe. And so what can happen is we can absorb energy. So this is called the ground state because the electron here is in the lowest possible orbit. But what you can do is you can excite the electron. But the problem is you can't excite the electron to any orbit. The electron has to be excited to the next allowed orbit. The next allowed orbit is way up here. And so if you don't have enough energy to excite the electron, it doesn't make it to this level here. And so let's say you excite a little bit, it's just going to fall back down. you have to excite it all the way to here, and then it will catch. And so you can excite the electrons either with photons. This is showing a photon or wave of light here coming in to excite the electron up here. Or you could excite it by kinetic energy or whatever, using heat or flame. You excite the electron, and so now we have an electron at the second level. The electron doesn't stay excited forever. Eventually, it's going to drop down. So in order to excite the electron here, this is in moles. So the energy is actually very small in terms of joules, 10 to the minus 18 joules per atom, but we don't necessarily always look at atoms. Sometimes we look at moles of atoms, and here it's 984 kilojoules of energy absorbed. Well, it turns out if it takes 984 kilojoules to promote the electron here, when the electron falls back down, it's going to release that because energy is conserved, so we're going to lose. This is the negative part here. It's going to be exothermic. We're going to lose that energy. And this energy is in the form of light. And so what has 984 kilojoules worth of energy per mole of light? We can think of moles of light because we think of a particle of light, although light doesn't have mass. We can think of a particle of light as a photon. So if we have a mole of photons, then 984 kilojoules per mole of photons, these packets of light, is ultraviolet light. I'm not going to have you guys, in Chem 1A we learn some, or we try to memorize some of the energies, you know. So we try to memorize the energy cutoff for violet, and we memorize the energy cutoff for red. That way we can make some predictions, you know.
What's the definition of photon again?
What's that?
Definition of photon.
The definition of photon is a packet of light. So a photon of X-rays versus a photon of red light of different quantities of energy. And so a particle of, quote unquote, particle of light that is a particle of X-rays is different than a particle of red light. And so a particle of X-rays packs a lot more punch, whereas red light is a lot less energetic. And so we can think of it in different ways. Like one way of kind of visualizing it is like a gamma photon would be like a bullet, whereas a radio wave photon would be like a ping pong ball. And so what would you rather be struck by? You know, a ping pong ball, like a radio photon, or a gamma ray photon, a bullet, you know. Well, they pack different amounts of energy. Well, this turns out to be in the ultraviolet. And the pattern is also observed in ultraviolet. You know, but you can't see it with your eyes, but you can see it with detectors. And we see lines in the ultraviolet, and these lines would correspond to these, what we call electron transitions. And so the line spectrum arises from transitions of the electron from step to step. And we have lines in the ultraviolet, visible, and the infrared that are observed, and all those lines fit the same mathematical equation. They all fit the Rydberg law, or the Rydberg equation. And so it doesn't show it here, fortunately, but let me show you the H atom spectrum. So we can map out all the possible steps. So for example, this is the first step here. And all these are pretty big energies, you know, going from 1 to 2 or 2 to 1, 1 to 3. You know, it doesn't have to go step by step. It could jump up. So for example, we could go from the first floor to the second, third, fourth, fifth, sixth, seventh, eighth, ninth, all the way to infinity. If we go from the first floor to infinity, we've just lost the electron. Now it's infinitely far away. We call that ionization. However, in this, all these blue lines correspond to ultraviolet. Those are all kind of high energy. And likewise, when we step down, we could jump, different steps. And we might not step down all the way here. So for example, here, let's say instead of the third floor to the first floor, here, third floor to the first floor, we go from the third floor to the second floor. If we go from the third floor to the second floor, then that turns out to be the red line in hydrogen. So this is the red line, and if we go from the fourth floor to the second floor, that's the green line. And if we go from the fifth floor to the second floor, that's the blue line, and then the sixth floor to the second floor, that's the violet line. This is called the Balmer series. The Balmer series is the visible. The Lyman series is in the ultraviolet. In the Paschen series, this is in the infrared. Paschen, Lyman are the people who discovered the lines. Lyman discovered the lines in the ultraviolet, and Paschen discovered the lines, I think, in the infrared. Balmer discovered the lines in the visible. The visible was discovered first, obviously, because those are visible. And then we could have more floors. Of course, we don't have to stop at the sixth floor because we can go all the way to n equals infinity. Now, the radius is not shown accurately here because the first orbit and the second orbit is 4 times further, and the third orbit is 9 times further. And so this is not accurate in terms of the orbits, but for energies, it's okay. Let's see if there's any other better ones here. So if you take a look at the Balmer, you don't have to know the names Balmer.
Whatever you do it for less at Harbor Freight. If you look around, everything is inspiration. My best friends and I own Pirate Worldwide. We're on a mission to discover as many ideas.
It'd be cool to see this by animation,
video,
but
I'm going to focus on
I
Bohr's
want to
model
see
of
the ads.
Now, he proposed that
This is a Rydberg law. This is the mathematical
So that's how
equation
you-
describing it. Let's see if this guy has some animations that we could see.
He doesn't have animations.
No animations.
it even involves a lot more. And then the fourth
Yeah, no animations.
is the third energy
fortunately.
level. Let's say from 5
But he's
to
talking
3,
about the Balmer
or 4 to
series.
3.
This is.
This is known as
I thought there was an animation
Pashkin.
in with the book, but we don't need an animation, I guess. The animation just shows an electron dropping from the third floor to the second floor and emitting a red photon. And then from the fourth floor to the second floor, emitting a green photon. And the fifth floor to the second floor, a blue photon. Sixth floor, second floor, a violet photon. Seventh floor to the second floor is the ultraviolet. And you can't see the ultraviolet, etc. So the question comes up is, why are the other orbits forbidden? Why are all these orbits forbidden? And do you know what the answer is? Hmm? No, the answer was, have you ever heard of a postulate? Postulate? Like a mathematical postulate? A postulate is just taken without proof. We postulate that. And so Bohr postulated that these were forbidden because they're forbidden. And that's what's observed. And there's no, you want a reason, but There's just really no reason other than that's what's observed.
And like quantum mechanics, it's like you don't disprove it, so it's like true.
What's that?
If I'm mistaken on like quantum mechanics, where it's not disproven, so it's just assumed true.
You just assume that's the way it is. That's the way it is. Well, it turns out, okay, this was very successful because that Rydberg equation describes all the lines, whether it's Balmer, Paschen, whatever, Lyman, doesn't matter. The Rydberg equation worked. Well, the problem is this. When they tried to apply this to helium, it failed. And it failed for every other atom on the periodic table. So this only worked for one atom on the periodic table, and that was hydrogen. They tried it for everything else, but they couldn't come up. Mm-hmm.
These two equations are only used for hydrogen.
Yes. These two equations are only used for hydrogen here. And the transition is called delta E. Delta E is equal to E1, which we call the Rydberg constant, times 1 over n final squared minus 1 over n initial squared. This is the Rydberg equation or Rydberg law. We're looking at steps. The steps between 2 and 3 would be final would be 2, initial would be 3. So if you drop from the third floor to the second floor, this would be the energy involved. It's a pretty straightforward equation. It's just taking En final minus En initial. Some of these equations are still valid in quantum mechanics. For hydrogen, this one is, and this one. But it turns out that this is wrong. This is wrong. So Bohr theory, this actually turned into a theory. The Bohr theory had to be modified because it didn't work. And so the Bohr theory was replaced by, do you know what theory it was replaced by? Quantum theory, exactly. So certain aspects of the Bohr model were retained. And so these are the contributions of Niels Bohr. Suggested reasonable, well, it turned out it was wrong. So I don't know how reasonable that is. But this is reasonable here. This is good. Introduce the idea of quantized electron energy levels in the atom. This is correct. And it's still correct. Levels in modern quantum theory appear as principal energy identified by n. And so we still have n equals 1, n equals 2, n equals 3. And this equation is still correct. This equation survived. What did I do with equations? In modern quantum theory, this equation is still correct here. However, this equation is wrong because there are no orbits. No orbits in modern quantum theory. Mill one's fine too. But what happens is quantum mechanics simplify for the hydrogen atom, and it spits out these equations. But for more complex atoms, it doesn't simplify so much, and the equations are a bit more complicated for helium and the other atoms. It turns out that when we look at the Bohr model, the Bohr model says that energy only depends on the variable n, where n can go from 1 to infinity. Well, the variable n is still there. We call it the principal quantum number. But there are more variables that we have to consider. So we have to look at we have to look at the quantum mechanical model of the atom. Quantum mechanical model, the biggest difference between the quantum mechanical model and the Bohr model is that we have to get rid of this idea of orbits. If we eliminate the orbits, then we're okay. But if we eliminate the orbits, then what's going on? And so here we get rid of orbits, and then we replace those with something else. What's going on is we have something called orbitals. I know it sounds like orbits, but it's different, quite a bit different. And so we replace orbits with orbitals, and then we're okay. Orbitals are a description of the electron. What do you want to know about the electron in an atom?
I guess those 4 feet below was below.
What do we want to know about? I'm sorry, go ahead.
Those 4 things listed below.
Hmm?
Those 4 things listed below.
No. Those 4 things listed below are going to tell us what we want to know about the electron. What do we want to know about the electron?
This structure.
Well, what did Bohr tell us about the electron? It told us the energy of the electron, the allowed energies and the forbidden energies, and what else? It told us where the electron is located in the atom. And so that we call position. So there are 2 things we want to know about the electron. Where is the electron and how much energy does it have? And then what are the allowed energies and what are the forbidden energies? So the orbitals are given the symbol psi, it's the Greek. And then we have 3 variables that the orbitals depend on. N, L, and M. And so each orbital that's allowed for an electron will have an N, L, and M value. These orbitals come from some modifications that they did. And so I'm going to do a little bit more about quantum mechanics here. A little bit more is this. When we went from the Bohr model to the quantum mechanical model, we added 2 important things here. One contribution came from this person, de Broglie, who talked about wave-particle duality. Of everything. So for example, light has wave-particle duality because of the photons, you know. Light is a wave, but it also has, it comes in little packets, and these packets are photons. And so we can think of photons as being like a particle of light. And a gamma ray photon packs a lot more punch than a red photon, say. Well, electrons we think of as particles, but electrons have wave properties as well. So light has wave-particle duality, and matter has, light is energy. Here, energy in the form of electromagnetic waves. And matter has wave properties too. We just don't notice the wave properties. So if you throw a baseball, do you know the baseball has wave properties in addition to? So for example, a baseball behaves like a wave. Well, how does a baseball, if you throw a baseball, let's say at 60 miles per hour, how does that behave like a wave? Do you see it oscillating? You don't really see it oscillating because the frequency is so high. I mean, the frequency is so high that it just looks like it's just moving continuously. In other words, the wavelength is incredibly short. Because the wavelength doesn't have any impact. Yeah. And so you don't notice the wave properties of this because lambda is so small relative to the size of the ball. And so lambda, which we use as a symbol for wavelength, is much, 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 much smaller than the size of the ball. And so it's not really confined. Because normally when we think about it, like if you're in a baseball stadium, can this ball be thrown? I mean, are there any forbidden speeds? No, all the speeds are allowed, right? No, forbidden speeds. And so one way I think about this is like, at SeaWorld, let's say, if you have a killer whale, and the killer whale's in the ocean, so you have a killer whale in the ocean, that's like a baseball in a baseball stadium. The killer whale is going to have a frequency. It can kick the tail back and forth, let's say, and there's locomotion. And so could the killer whale move at any speed it wants in the ocean up to its maximum speed? Yeah. Are there any forbidden speeds for the killer whale? No. So here, when it kicks its tail, it can kick it and it has plenty of space. But what happens if we confine it in a small box? That is, what happens if we put the killer whale into an aquarium? And let's say the aquarium is very small. Then maybe in this aquarium, can this whale have any speed? It depends, because let's say each kick of its tail, it's got to do something. So maybe one kick of its tail, it's already at the other end. And so when the whale's confined in a small box like this, then how many kicks of the tail it has is very important. There are going to be certain allowed ones and certain forbidden ones. Does that make sense? No way. And so here, when you confine a whale to a small box, all of a sudden, how many kicks of the tail you have come into play. And now it doesn't have that freedom that it once did. Well, that's the same thing with an electron. If we put an electron in a piece of metal, the metal's like an ocean. In fact, we call this the electron sea model. The electrons in a metal are like the ocean. And the electrons can move anywhere in the metal. So if it wants to move very fast, it can. If it wants to move very slow, it can. It's not really confined. And so electron in a piece of metal, we have a continuum of energies that are allowed. But if you confine the electron in a tiny box, the tiny box is called the atom. Then there are problems because the electrons have wave properties like the tail of the killer whale. The electrons will have wave properties here. And now the electron confined to an atom, which is a very tiny box, is going to have this happen. And so let's talk about, what am I talking about this? Here it's going to be behaved quite differently, because now when we look at the wavelength for an electron, let's say it wants to go back and forth. If it wants to go back and forth, then there are certain things that are allowed and certain things that are forbidden for these waves. When you confine a wave like this, we'll call this the energy. Think of an instrument, and you have a string here. When we pluck the string, not every sound is allowed. Did you know that? If you pluck the string, we're constrained because the string has wave properties and it's got to be attached at one end and attached at the other end. So when the string vibrates, we'll have a fundamental frequency like this. This would be called the ground state. And so the string can vibrate here, like this. But the next allowed energy is not just a little bit more. The next allowed energy is up here where we have to fit a full wavelength in there. So this is called a half wavelength. The next allowed energy is a full wavelength. And so we'll call that 2 times 1/2 lambda. This is 1 times 1/2 lambda. And then what's the next allowed energy? Do you know what it is? 3 half wavelengths. So we'll call it 3 times 1/2 lambda. And so this is n equals 1, this is n equals 2, this is n equals 3. But what happens if we try to put in, let's say, 1.5 times half lambda? What happens is we end up with something that doesn't quite sync up here. So is this allowed? No, this would be forbidden. We can't vibrate the string at this frequency or this wavelength because this is not going to attach there. So if we try to get this one, this is in between this and this, it's not going to happen. You see that? So when you confine a wave to a small box, this is what happens. An electron behaves like a wave. And so what we can see here is, based on de Broglie, we're going to expect quantized energy levels. Not any energy is allowed. And so this is forbidden. And the forbidden would be n equals like 1.5. That's forbidden. And so, forbidden. Anyway, what we're going to see is that the blues are allowed here. This is called a one-dimensional standing wave. One-dimensional standing waves are quantized. So let's take a look at two-dimensional standing waves. Try to turn up the sound. So the plate there, this is the plate, and the plate can only vibrate at certain frequencies because of the confinement. And so they're pouring sand on there to see. And so when we think of waves, we have positive and negative amplitude, and so the sand is going to collect where it dips down, and there's going to be no sand where it dips up. So we have positive amplitude, which you call plus, and then negative amplitude, which you call minus, and positive amplitude and negative amplitude. And so this is the waveform for this plate. This plate can't vibrate at any frequency it wants. The plate has specific frequencies that it vibrates, and those are called allowed. Everything else is forbidden. And the frequencies of the plate depend on the material it's made out of and how big it is. So that's forbidden, 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 and then that's allowed. These are getting higher and higher in energy. What's that?
What's the surface that they're using?
The what?
The surface?
The surface is, I think, just a metal plate. I don't know what it is. I think it's just a steel plate or something. These frequencies are kind of important. Like now, when they do structures, like they build structures. You heard of the Tacoma Narrows Bridge? The Tacoma Narrows Bridge also has allowed and forbidden frequencies. You haven't seen the Tacoma Narrows Bridge?
We're in Tacoma, Washington, and behind us is the Tacoma
1950 and the other in 2002.
or Galloping Gertie.
What's
It
that?
was opened on July 1st, 1940. Because of windy conditions,
Yeah, do you see the bridge can oscillate at certain frequencies, and it just so happened the wind hit it just at the right frequency. And so this is the frequency of oscillation for the bridge. And then they kept adding more and more energy to it, and eventually it just collapsed. So they hit that. So nowadays what they do is they test the structures. They test these as models. They make sure what is the resonant frequencies of this, and they got to make sure that it's not going to happen. Whatever the frequency of the structure is, they got to make sure that the winds or whatever else make it all forbidden. In other words, they don't want an allowed frequency to come out. Otherwise, they might have a disaster like this happen again. And so there are certain ways you can check the frequency of structures. So this is the same kind of thing. You got to just make sure that these frequencies aren't hit. Otherwise, it's going to start vibrating. If you don't want it to vibrate, if you want it, this would be like a drum. If you want it to vibrate, then you got to make sure you hit it at the right energy to cause that. So one thing we notice is that at the higher and higher frequencies, we see more of these, what we call nodes, you know. Node is when you pass from positive to negative and you go through zero amplitude. And so this goes up and then down. And we get something like this. Well, if we treat electrons, electrons will have wave properties. And we'll end up generating things like that. What the heck? But these are three-dimensional. And so this is showing, these are orbitals here, representations of the orbitals. And so this is just one positive amplitude, like the first standing wave we saw in the string. This would be like the next one where it went up and then down. And so the orange is positive amplitude, the blue is negative amplitude. So we see that. You see different shapes. These wave. We call these wave functions. So here's some more. And so as we get to higher and higher energies, so low energy, this is the lower energy ones up here. And then as we get to higher and higher energies, you see more. We call these lobes, you know, these areas, amplitude here. And then the blacked out regions here we call nodes. Just transitions from positive to negative amplitude. And so here, the lowest energy one is here. Then we have these higher energy ones here. And the color coding is just to show you the amplitude. Positive, negative, positive, negative. So positive amplitude here. And we describe these using the symbol psi and three variables, N, L, and M. So de Broglie looked at the wave properties of the electron, and then there's one other thing that we need to know in going from Bohr to quantum mechanics. It's a bad connection. This is wave-particle duality, and then we have Heisenberg. Now Heisenberg, we'll just say some of Bohr model was retained and modified. Heisenberg is most famous for the Heisenberg uncertainty principle. The Heisenberg uncertainty principle states that for us, the end result of this is that we can pinpoint the energy but position is not pinpointed. We look at it in terms of a probability of finding the electron. This probability is given off as what we call the electron cloud. So one way of thinking about the electron cloud is like this. You have to think about the electron as being like a bird, and the nucleus is the nest here. So let's say we find the electron here. Can you tell me where the bird's going to be at in, let's say, 5 minutes later? Can you tell me where the bird's going to be at 5 minutes later? So that's the same thing. Can you tell me where the electron's going to be at 5 minutes later? It's like trying to ask, you know, do you know where the bird's going to be 5 minutes later? And so what we do is we know the energy of the electron, and the energy of the electron says that it can't be too far away. And so the same thing with the bird. The bird might be here. It might be here. It might even be out here. But the further we get away from the nucleus, the lower the probability. And so most of the time the bird is going to be somewhat close to the nest. And so what we end up generating is something of an electron cloud. The electron cloud tells us this. The density of dots are going to tell us the greatest probability will be at the highest density of dots. The density of dots is just telling us that most likely the bird's going to be around here. And then as we get farther and farther away, the density of the dots decreases. This is called the electron cloud. In the electron cloud, the density is going to go to 0 at infinite distance. So, yeah, the electron can be kind of infinitely far away, but the probability of that is so small that it's unlikely. In other words, what we want to do is we want to capture like 95% of the dots, you know, and then call that a boundary here. The boundary would be, let's say 95% of the dots are inside. That means 95% probability of finding it within this fence, and there's going to be a 5% probability of finding it outside that fence. This gives us an indication of the size of the orbital. Of course, if it has more energy, it's going to increase the size because the electron can be further from it. And so this is the idea of the electron cloud. We know the energy of the electron, we just don't know exactly where that electron is, and we can't predict its trajectory, its path. In the Bohr model, you could predict the path of an electron because in the Bohr model, the electron just orbited around the nucleus. From the Schrödinger equation, we're going to get the energy and position of all allowed orbitals. And so we do the math of the Schrödinger equation. You need calculus to do this. And then it's still very difficult. You could do this without too much difficulty for the hydrogen atom, but anything more complicated is going to be tough. And then we get the answer. The answer to the Schrödinger equation is the orbital. We see a certain pattern, and the pattern is going to depend on 3 variables, n, l, and m. These are the allowed states for the electron. So our book doesn't get into it deep enough. So we have to supplement the book. N, L, and M are called quantum numbers. So in your Chem supplement, you're going to have this section called quantum. And the following discussion supplements the textbook material. So you could read about this wave mechanics. But basically what we want to know is there's a simple pattern, and what we want to know is we want to know what is the pattern. We're not actually going to do the math. Somebody else did the math. All we're going to do is the pattern. And so the pattern is going to depend on 3 variables. The first variable is called n. And n is called the principal quantum number. And this is kind of the step. You know, what step are you on? These are the allowed ones. Everything else is forbidden. And so we could be on the first, the second, the third, the fourth, all the way up to infinity. And so we need to memorize this. N is equal to 1, 2, 3, 4, etc. That's a mathematical restriction because if you put in any other n value into the Schrodinger equation, it fails. And so these are the only n values that work in the Schrodinger equation. And we think of n as just being the energy level. The next quantum number is L. L tells us the shape of the orbital. In the Bohr model, the energy only depends on n. And that's okay for hydrogen. The hydrogen atom, the energy only depends on n. But in quantum mechanics, the energy depends on both n and L, the shape of the orbital. We give different letter designations to the shape.
What is n represent again?
The energy level, like how many steps up. The higher the n, the higher the energy. And so we just call that the energy level. L represents the shape, but it's mathematical. And so when you plug in an L equals 0 in the Schrodinger equation, it works out. That's allowed. And so, for example, L equals 0. 0 has a spherical shape. An L equals 1 has a figure 8 shape. An L equals 2 has like a 4-leaf clover shape, etc. And we give letter designations to these as well. So an L equals 0 is called an s orbital. An L equals 1 is called a p orbital. An L equals 2 is a d orbital. An L equals 3 is an f orbital. And they're going to have different shapes to them. It's called the azimuthal or the angular momentum quantum number. M is the magnetic quantum number. And M tells us how many orbitals of that shape we have. So for example, if we have a figure 8 orbital, there are 3 of them because they can be aligned with the x, y, or z axis in a 3-dimensional coordinate system. And so M tells us the number of each type of orbital we have. If we have an s orbital, then we only have 1 of them that are allowed. So these are the allowed values. So it goes from minus L to plus L. So if L equals 0, we go from minus 0 to 0, there's only one value, 0. So there's only one of those orbitals. But if L equals 1, we go from minus 1 to plus 1, going by integers through 0. So it goes minus 1, 0, 1. There are 3 of them. Minus 1 corresponds to an axis, 0 corresponds to another axis, and plus 1 corresponds to another axis. So they're oriented in 3-dimensional space. If we go to L equals 2, there are 5 of them. We go from minus 2 to minus 3, and no, not minus 3. We go from minus 2 to minus 1 to 0 to plus 1 to plus 2. So that's 5 values.
And I think it's the number of orbitals.
Yes, number of orbitals of a given shape. There are other mathematical patterns here, which I'm going to skip for right now. And what we're going to do is we're going to generate a list of all the allowed orbitals based on the restrictions of the quantum numbers. So these are mathematical restrictions that come from the Schrodinger equation. So for example, if n equals 1, then L can take on all values from 0 to n minus 1. And so the only value of L that's allowed is 0. Because n minus 1 would be 1 minus 1 is 0. That's a max. So this tells me I have, at the first energy, I have a shape 0. That shape 0 is called an S, and it turns out it's spherical. How many of these spherical ones do I have? Well, I'm going to go from minus L to plus L. So minus 0 to plus 0 is only one value. And that one value, that means I only have one of these spherical shaped orbitals at the lowest energy. At the next energy level, which we call n equals 2, then I have two shapes that are possible. Because the shapes that are possible are going to go from 0 up to a max of n minus 1. n minus 1 is 2 minus 1 is 1, so that's my maximum value there. And so I have a 2, 0 and a 2, 1. A 2, 0 is a spherical shape, and that spherical shape, there's only one of those. However, a 2, 1 varies from minus 1 to plus 1. So minus 1 to plus 1, I have three values that are possible. I have a 2, 1, negative 1, a 2, 1, 0, and a 2, 1, positive 1. And then that's it. When I go to n equals 3, I end up with three possible L values. That is, I could have 0, I could have 1, I could have 2. 2 is the max because the max is n minus 1. There's 3 minus 1 is 2. So this is going to be a spherical shape, this is going to be a figure 8 shape, and this is going to be like a 4-leaf clover shape. For the spherical shape, I only have one because that goes from minus 0 to plus 0, so there's only one value allowed. For the figure 8 shape, there are three values allowed because it goes from minus 1 to plus 1 going through 0. So that's three values that are allowed. Each of these is a code. One of these is the x-axis, another is the y-axis, another is the z-axis. When I have this clover leaf, there are actually, we can go from minus 2 to plus 2, so that's five values. Minus 2, minus 1, 0, plus 1, plus 2. And these five values define planes where the clover leaf. We can have the clover leaf in the xy plane. We can have it in the yz plane. We can have it in the xz plane. And then there are two extras that are in there as well, which don't exactly look like clover leaf, but essentially they're all the same energy. When we go to n equals 4, so we're at the fourth energy level, then we have four shapes that are allowed. The spherical shape, the figure 8 shape, clover leaf shape, and these ones are more complicated. Like a 6-leaf clover or something like that. And when we go to these, then there are going to be more of that shape that are allowed. And so these are what we call the allowed energies. And the allowed energies, we don't build a table like this. The allowed energies, what we do is we build what's called an orbital energy level diagram. This is the orbital energy level diagram, and you should be able to draw this. Can you draw this? What's that?
It's just a bunch of lines.
Just a bunch of lines. But we could draw this. I'm not going to draw the whole thing because there'd be an infinite number of lines we'd have to draw, and it's too much. we should be able to draw up to a certain point. What is that point?
4?
Yeah, we want to draw up, not the entire 4, n equals 4. It's a bit more tricky than that. So for the hydrogen atom, the energy just depends on N. So what we can do is we do this for the hydrogen atom. We have the psi 100, and in our code we call that the 1s orbital. And this is going to be energy here going on. And then that's it. The next allowed would be psi 200. This is NLM. NLM. And then we have the psi 2, 1, negative 1, the psi 2, 1, 0, and the psi 2, 1, 1. As far as the orbitals, the orbital shape is going to be given by the electron cloud distribution. And we just confine it to the 95% fence. So if I look at just the 95% fence, it looks like that. The 200 is going to be bigger because it has more energy. And it also has what we call a node in there, like that. I'm not going to get into it. And then the figure eights depend on what axis it's on. So I could have one on the x-axis, one on the y-axis, and one along the z-axis. And so what we do is we call this one a 2s orbital, and then we have 3 different 2p's. We could have it like a 2px, a 2py, a 2pz, something like this. I forgot if negative 1 was x or whatever. Doesn't really matter. Or we just call these the 2p orbitals. We have 3 of them. These are the 3 2p orbitals. And then we go to the n equals 3. When n equals 3, I could have different L values. And so I'm showing them here. L equals 0. M is equal to 0. That's this. And then over here, I have L equals 1. M can equal negative 1, 0, and 1. That's what I have here. Negative 1, 0, and 1. And so this is going to be my psi 300, which the psi 300 is just going to be a lot bigger. And actually it has 2 of these nodes where it passes between positive and negative amplitude. These p's are going to be much bigger. This is not a very great drawing of these. But the shape is a bit more complicated. It's not as simple. And those we can identify as this. This is going to be the 3, 1. I'm going to get rid of the psi and just use NLMN. 3, 1, negative 1. 3, 1, 0, and 3, 1, 1. But not only do we have L equals 1, we have a max L value of n minus 1. So if n is equal to 3 here, then the max L value is going to be 2. This is n equals 2 here. This is n equals 1 here. If L equals 2, then my M values are going to be minus 2,
I'll wait too.
yeah, minus 1, 0, 1, 2. And that gives me 5 lines, 1, 2, 3, 4, 5. And that's going to be defined as 3, 2, minus 2, 3, 2, minus 1, 3, 2, 0, 3, 2, 1, and 3, 2, 2. I just wrote this up here.
Is
So.
this a graph?
Is that?
Is there the x and y axis?
Right, these are in planes. Do you want to see what they look like?
It looks, it's like a graph. It's a weird graph.
These are what they look like. Actually, just one of them here. Oh, actually more than one. Well, they didn't show enough of them. We call these d orbitals.
This is just to be on the same page. This is only for hydrogen, correct?
Yes. And so they're defined by the planes. Here's the 1s, 2s, 3s. Here are the p's. Here are the d's. This is in the YZ plane. This is in the XY plane. This is an XZ. So they say DYZ, YZ plane, DXY, DXZ. But we have two more. This is the DZ squared, which looks like a figure 8 with a hula hoop. And then this is the DX squared minus Y squared, which are right on the axes. And so these are the 5 d orbitals, what we call d orbitals, or L equals 2. So we'll stop in a minute. So we have the ways of describing it. So a 300 orbital is called a 3s, and these are the 3p orbitals here, and then these are the 3d orbitals here. L equals 3 is forbidden, because the max L we could have is n minus 1. And so that's forbidden. So we have to go up to the next one, which would be n equals 4, etc. So we're able to generate all infinite orbitals. There's some more patterns here. So for each n, we call these levels here, and we call these sublevels here. So when we're at the first level, there's only one sublevel. When we're at the second level, how many sublevels are there? 2 sublevels, the S and the P. When we're at the third level, how many sublevels are there? 3. And so that's another mathematical pattern. The mathematical pattern are there are n sublevels for every n. For each n. How many orbitals are there in each sublevel? There are 2L plus 1 orbitals. These are other patterns. In each L sublevel. How many orbitals are there in a level? There are n squared orbitals in each n. So for example, n equals 4, how many orbitals am I going to draw?
And
16. If I'm at n equals 10, how many orbitals? 100. Are they easy to figure out? Yeah, they're easy to figure out because they all fit this pattern. We just extend it.
only for hydrogen.
Only for hydrogen, right?
Is similar with the other elements or no?
Yeah. So we'll talk about all the other elements next. We'll take a break now. Then we'll talk about the other elements after the break. From the quantum mechanics theory, we come up with this. It turns out that the pattern that we see depends on if it has a single electron or multi-electron. If we have a single electron, then the 1s, the 2s, the 2p's, 3s, 3p, 3d, 4s, 4p, 4d, 4f. 4f is going to have 7 lines. 3, 4, 5, 6, 7 lines. This is 4f. It's going to have 7 lines because we go from -3, -2, -1, 0. So -3, -2, -1, 0, 1, 2, 3. That's where the 7 lines come from, etc. In other words, the energy just depends on n. And so the Rydberg equation and everything else works because the transitions are going to be from the 3 to 2, we get the red line. From the 4 to 2, we get the green line. From the 5 to 2, we get the blue line, etc. So we get the lines from electrons. And so what happens in the red line is an electron's excited. Let's say an electron gets excited up here and then drops back down. It's going to emit red photon. In the blue line, an electron gets excited to the 4th floor and drops back down to the 2nd floor. Oops. That's going to give us a blue line.
Why don't we go back down? Why don't we go down to
Or
the
green,
first
sorry.
line?
What's that?
Why don't we go to the first line?
We do. Except you can't see it. It's ultraviolet. And so an electron can go down to the 1st floor, but you need a special detector to observe it. So, UV detector. However, for multi-electron atoms, it's a little bit more complicated because the energy depends on N and L. So not only does it depend on the level, but it also depends on the shape. And this is because the electrons interfere with each other. And what happens is we end up with a pattern that looks like this, where the 2s and the 2p are no longer the same energy. The 2p has a slightly higher energy here. And then we have the 3s here, and the 3p have slightly higher energy here. But the 3d get bumped up. And so what happens here is the 4s comes next, and then the 3d come next in terms of energy. I'm spreading them out because I'm looking at different sublevels, the S sublevel, the P sublevel, the D sublevel. So the 3D's over here, and then the 4P is out here. However, the 4D are in the next, way up here, etc. And so we see a pattern that ends up looking like this. And what we see here is we see what we're going to call shells of orbitals. shells of orbitals will be closely spaced in terms of energy. So we call this the first shell here. And then the second shell is here. I'll do the second shell to highlight it. Would consist of these subshells, the S and the P. And then the third shell just has the 3S and the 3P. And then the fourth shell has just these orbitals here. Oops, I wanted to go blue. Yellow and blue make green. So let's make this green. Yeah. So we see the different shells. The pattern in the shells can be given like this. We come up with a pyramid. And the shell always begins with an S. And what we do in this pattern is we go like this. So the first shell is just one S. The second shell begins with S. So it goes 2S, and then it goes to 2P, and then stops there. The next shell begins with 3S, and then goes to 3P, and then stops there. And the next shell begins with 4S, and then we go to 3D, 4P, and then stops at 5S here. And so this is what we see. So there's very few, a single electron would be the H atom, the helium plus atom, or ion, or the lithium 2 plus ion. These are rare. They're synthetic. So this is pretty much just the H atom here. H atom is only one element in the periodic table, so what we want to do is we want to focus on the multi-electron and be able to draw that out. And so this is why we come back to this. Do you see this is the multi-electron here? In the pattern we get 1s, 2s, 2p, so you just remember this pattern here. And this goes through the first 4 shells of orbitals. And so first shell, second shell, third shell, fourth shell. That's different than the energy levels because, for example, n equals 3 would have 3 sublevels, the S, the P, and the D. But the D doesn't belong in this shell. The D belongs in this fourth shell, not the third shell like you would expect. And that's because the energies get all screwed up because of the way the electrons interfere with each other. And so if we see this, the pattern gets much more complicated. And so when we go to helium, the line spectrum of helium is way more complicated than the line spectrum of hydrogen. And that's because of all these additional energy levels here. And so let's take a look at the line spectrum for helium. Oops. Not that one. This one. I don't know what this overlay stuff. This overlay is just the colors of the rainbow, but these peaks here show the lines of the helium. These are more descriptive because these actually show the intensity here. Not all the transitions are equally probable, and so rather than getting just straight lines, this tells us more information. But I don't want that additional information. I just want something simpler. So let me look for an image without all that additional information. So this would be an image without that. And so we see additional lines. And the neon, you saw a bunch of lines. there, mercury, etc. And so we have this. And so when we look at the line spectrum for helium, we can attribute these lines to a transition between orbitals, versus in hydrogen, it's a transition between energy levels. Now, there are some line spectra that are not very complicated, like sodium, but there are some complications. See if I have sodium here. Yeah. It looks like there's just one line in sodium. It's actually two lines. We call it a doublet. The sodium doublet here. And those could be easily described by transitions here, which we'll talk about. Maybe we'll talk about, probably won't. And so, sodium is simple, looks like simple, but it's more complex, and it's described by. This is just the visible portion. There's a bunch of invisible lines that we don't see in there. We've got sodium, we have mercury, lithium, hydrogen. Each of these is a fingerprint. Those fingerprints arise from transitions between different orbitals. And there are rules that govern the transitions, which we're not going to talk about. That's all part of quantum mechanics. You can use all those rules to generate the spectrum of this. And so to make a long story short, from quantum mechanics, we generate the allowed energies for the where did I do? For the electron, and these correspond to a certain probability distribution. The probability distribution has different shapes. So this would be spherical, this would be figure eight, that would be four-leaf clover type shape. And so that tells us the energy and the positions. We don't actually have the numbers on these, and you don't have to know the numbers. And you just need to know the three simplest shapes for this. When you look at the books diagram, this is no good, basically. And so figure 1114 is worthless. Don't even bother wasting time with this figure. It's a waste of time. So we're dealing with orbitals. The orbitals come from the Schrodinger equation. This is the Bohr model with orbits. And so one major difference between an orbit and an orbital is in an orbital we're going to have the electron cloud, the probability distribution. That's what we want. And so the electron could occupy an s orbital, it can occupy a p orbital, a d orbital, etc. This is showing many orbits. This is only showing one orbital over here. Usually we don't show it as a cloud. Usually we show it as a boundary. So 95% of the droplets of the cloud are contained within that boundary. 5% are outside. So these are what we call 95% probability boundaries. And that kind of gives us the shape. Since there's 5% probability, it just decreases the further you get out from the nucleus. And so that's the S shape, this is the figure eight, or the P shape, this is the D shape, which is the four-leaf clover shape, except for one of them. Just this one has a weird one. These are different energies of the s orbital. This is the 1s orbital, or the 100. This is the 2s orbital, the 200, and this is the 3s orbital. And so it just gets bigger, the probability boundary for that. There's more. It's a little bit more complicated than that. All right, I guess I'm not going to quite. Chapter 11 is kind of long, so what I'm going to do is I'm going to stop chapter 11 here. And then let's get some practice with chapter 10. And so this is the practice that we're going to do for chapter 10. Here. And blow this up. So why don't you try to work on this problem here? Did I forget to record this? No, I didn't.